Alright, hello friends, and welcome to a very exciting lecture. I'm excited to teach you about these things called hash tables. So let's get right on into it. Where we left off was, well, we noticed that it was not too hard to make a lookup table that goes from integer keys to any type's value. So I'll just use t there. I'll just make it a big cloud. Cloud 1, cloud 2, cloud 3, for example. And then every int can map to one of these. So maybe this was like 3, this was like 42, and this was like 78. And as long as you had a big enough vector, or array, of course, ... you could store all this stuff in there. You could store all the clouds. Oop, there's your clouds. So this can be any type, but it would really be nice if this could also be any type. And that's where we're going with this. So let's remember first how we squished our data into a lookup table. So remember that we've only got so many indices to work with. We've got, I don't know, index 0, 1, 2, 3, 4. Maybe you only have 5 things in your table, and you want to store integer keys of large sizes. Like, I don't know, maybe you're trying to map 1,284 to high, and then like 4,876 to mom, things like that. And I guess the question is, how am I going to put this somewhere in this table? So how do we squish it down so that this key maps to one of these indices? Okay, so let me talk about the problem just quickly. So the problem: large keys, small indices. Okay, that's the idea. The hash table is just a glorified lookup table that solves this problem through hashing. Okay, so this would be like the modulus hash. So this worked last time for us. It's a hash function that stores student IDs, and so let's be a bit more precise now. Let's talk about what hash function means and hash and all of that stuff. All right, so a hash, it's a way to generate a number from some type. And well, that number has to be very precise. So this is a hash function, by the way, hash or a hash function, whichever one you want to say. It's a way to generate a number given a value of a certain type. For well, before I get into an example, let's also go through the idea of it needs to be a special number. It better be one of the indices of your table. Okay, so there's technically 2 ways to do this. You can start the hash and then like shrink it down, or you can think of it all in one fell swoop, and that's the way I'm going to present it to you right now. The book might separate these two, and it's more precise to do that, but I'm going to put them together in your head this way. So you're getting a number from a type, and you're also shrinking it down to be one of the indices of your table. Okay, so that's the idea. So for example, maybe you take 1,284 to, I don't know, index 42, and you have like a size 50 array. Or maybe you take the string hi mom and you somehow make that go to index 24 of your array. Okay, you're turning types into numbers. It doesn't matter if it's a string, it doesn't matter if it's an integer. And for integers, at least, we noticed that modulus works pretty well. So modulus, the modulus operation, that's a percent sign, of course, always will can always take a number and shrink it into one of the valid indices in your array. So that's super nice. Say you had an array of size 50. So that means it has indices 0 through 49. If you just do mod 50, just take a number, I mod 50, always a valid index. That's super nice. Okay, that's not bad. Well, coming at this from other types, though, is a bit more interesting. So how can we make a lookup table for non-integers as keys? So we want to always make a number out of something. So our goal, again, is maybe we want a real phone book lookup table. I think that's all one word, right? Taking strings to ints this time. So instead of my number to my name, it's my name to my number. We want to go from Lawton to 8675309. Okay? That's the idea. So how can we convert from strings to numbers? Well, let's figure this out. Dun dun dun. Example time. So let's try and convert the string A to a number. Well, there are some ways to do this, and think back to maybe CSCI 40 where you learned about ASCII. So the ASCII table represents characters as numbers. Ooh! So if this is just a single character, I can use the ASCII value of it. I can hash my string of length 1 by just giving back the ASCII value. And so that'll work. Then I'll just have to mod it down again, of course. So that's not too bad. And okay, that's not too bad. So my hash function for strings, it can be, well, maybe I will take my first character, or take every character, and do something with its ASCII values. That's not too bad, right? Those are numbers, and I can combine them. So, for example, now maybe AB you'll take the ASCII value of A, which is, I have no idea, but look, we can find that out pretty quickly. And B is 98. So 97. So you got 97 and 98 to work with. You can multiply them, you can add them, you can do fancy things, convert them to very large numbers by using exponents. Something like that. So I've just shown you a way to take a string and make numbers out of them, okay? So this is a hash function for strings, so it's going to convert. That's what a hash function does. It's going to convert that type, strings, into numbers, so that I can then store them into my table, okay? They can be the keys of my table. That's beautiful, okay? So that's not too bad. So we can use anything. We can use anything as the keys of our table, and so it's always key value, key value. I should put this here, perhaps. So the index into your table is called a key, and the thing that you get out of it is called a value. Okay? Keys and values. Keys and values. You'll read about that. All right, so let's go back to the idea of just integer numbers for our table indices. we're taking ints and trying to map them down, shrink them down into other ints. Well, let's think of all the different ways we could store things. So it would be really nice to do this in class, but maybe you can just pause the video and I'll try and guess what the class might have been like. So what day of the month were you born? We can use that to index into a table. Okay, these could all be keys. And what I'm about to show you is that some values are better than others. Some ideas to store, some keys are better than others. But some keys are better than others. Okay, so what day of the month were you born? Maybe it was the 30th, maybe it was the 29th. I think all of us, maybe in this class, there might not be too many overlaps, right? There's a lot of days. Yeah, that's not too bad. So not too many overlaps there. What about your birth month? Ooh. Dun dun dun. If we try to make a table of 12 things, that's all we have to store, I think there's going to be a lot more in some months. Like, I was a Christmas present, probably some of you were as well. So that's going to look not as flat of a distribution. Some months, like September, are going to have a ton of birthdays, okay? And then what about birth year? Well, I think that's going to be even worse because most students, on the whole, are going to be like, what, 18 years old right now? So there's going to be a huge jump in like 2002 birth years, okay? Maybe there's some more in other places, but there's going to be a large amount for birth years. So if we wanted to use any of these as indices for our table, maybe no overlap here, so maybe no overlap. Like pretend we wanted to store like birth month to student name in this class. So there's going to be multiple students that had birthdays in the same month. I don't know. There. That's not too bad. Maybe we can get away with clashes for days of the month, but birth month we're probably going to get a few clashes here. So we can't like store them both in the same index, right? Boop, boop, boop. We're trying to both store them in like index 6. We can't put two things there, can we? That's going to be a problem. And then birth year is going to be even worse, because then we're going to try and store like a bunch of people to 2002. And the list goes on. Okay, so there are some keys that are better than others. And, well, maybe you're forced to use one. You're going to end up with this thing called a collision. Okay, so a collision is when there are two things trying to map to the same place. So you're trying to take 2 to 42, and you're trying to take 2 to 73, and, well, you can only put one thing here, right? 0, 1, 2, 3, 4. This is your vector, your lookup table. So do you put 42 here? Do you put 73 here? What do you do? And we'll talk about solving collisions. All right, so hash table terminology. Here's my lookup table. It takes keys to values, and every key is shrinked by a hash function to an index. Maybe I should write that on the arrow, actually. Hash function into an index in the table, in our lookup table, of whatever size you give it. And at that index, you can put a value there, okay? So you have a big long vector with a bunch of indices where you can store things, okay? And each index is called a bucket. Okay, so that's a bucket. In your lookup table, each index is known as a bucket. Then a hash function we talked about, that's just a mathematical function that you write that takes a value of any type and converts it to an integer, and eventually you can shrink that down. Okay. To shrink it down, but we'll just talk about the conversion to an integer part. That's really what a hash function is. And another key thing of a hash function is it needs to take the same value to the same index every time. Because maybe your hash function h took 42 to like 7 a second ago. Maybe you're using like a random number generation, and now you're about to take 42 to index 6. That's going to be an issue if you ever try and look that up ever again. So we don't want that. No. And then a collision is when you have two values that map to the same place. All right, so that's what we have. So let me draw just quickly an example collision, an example hash function, example table, and get this all in your mind. All right, so let's say I'm trying to store these keys and these values. Okay, let's say key 10 or key 5. I want to store blah, and at key 10 I want to store, I don't know, foo. All right, so that's what I want to store in my hash table. Here it is. It's a lookup table of size 5. Okay, and all right, my hash function h of x equals x mod 5. Okay, because that's the size of my table. So it's going to take this key to by the hash function, it'll take the key to, all right, what's x mod 5? Well, it goes in cleanly, remainder 0, index 0. And you can see where I'm going with this. By the hash function, it takes 10 also to 0. So the first time I add this first thing, I'm going to add blah to index 0. And then I'm going to try and add to index 0 again foo, but there's no room for foo. What do we do? Okay, so let's handle these collisions. So there's some different options that you have to go and fix the fact that two things are trying to go to the same place. And the terminology is very confusing. I'm sorry about this. But the first one is called open hashing, and then the other one is called closed hashing. You're going to implement open hashing in your lab, but here is open hashing. If we had, let's see here, we had our vector v, and by the way, I had to stop this because I had an extra index there. It's only supposed to be of size 5, so it only goes to index 4. Excuse me. V goes to index 4. 0, 1, 2, 3, and 4. And so open hashing, instead of storing keys in the table, like blah, and now I have no room for foo, it stores them outside the table. So it's like open, the door is open, you can store things outside the table if you need to. Closed hashing is the door is closed, you cannot walk outside the table, you have to use another index. Okay, so with this you can use a list, and with this you can just find another index. To use. Okay, so that's the idea. So let me give you an example. So at index 0, instead of storing the value, I store a pair. I store a list of pairs, actually. So I'm going to store the fact that foo went to, I'm going to store the fact that 5 went to foo, right? I know it was blah, wasn't it? 5 went to blah, and then when I try and add at index 0 again, I'll add another pair, okay? I'll add the fact that 10 went to foo. And now suddenly I've stored information, okay? That's super nice, because now I can store as many things as I need and always go back to them. If I get taken to index 0, I just figure out which one of these was the key that I was searching for, 5 or 10, and then I can give back the value that was searched for. Okay, I'll give you an example of this if it's still a bit fuzzy. Closed, on the other hand, is like, oh shoot, I can't walk outside the table. I can't use lists or anything. So if blah is going to index 0, well, and I'm trying to add foo somewhere, well, it can't go here, so maybe I'll just try the next one, and that's where I'll store my foo. Okay, so believe it or not, open hashing is a bit easier to implement, so that's what I'm going to have you implement in your lab. So these are the two ideas, and yeah, I think that's where I wanted to put you there. And let me give you a reverse phone book example now. And then we'll code that up. How about that? So let me try and store, I don't know, mom to 555 5555, and then my number can of course be 8675309. And so these are my keys. They're strings now. Gotta make them int somehow. And these are my values. So let's pretend I had a size, I don't know, a size 3 array. 0, 1, 2. And let's pretend that these somehow both hashed both to 0. I'm going to implement a hash function that does that, just a simple, stupid hash function. And then we're going to store these values inside our hash table. So I'm going to show you insert, and I'm going to show you lookup. Remove isn't too bad. So honestly, I'm doing most of your lab for you, if you think about it, but I want you to be a bit more fancy than this, of course, and you're going to implement them as like classes. So alright, so we're going to take keys to values, and the keys are strings. So if mom hashed to 0, that means at index 0, I'm going to store this value. But because multiple things can hash here, we're storing lists of things. So at each index, I'm storing a list that starts out empty. Alright? And we're storing lists of pairs of things. Okay? So let's see here. Boop, boop. I'm going to store, I don't know, mom, it's a pair, with, I guess I need more room, don't I? Yeah. Let's do this. Now I have more room. First I'll store the pair mom and the number 555 5555. A lot of 5s. And so then, after inserting just this is what my hash table looks like. And then when I want to store Lawton, this is the reason why we have to store these keys, is, alright, boop. I'll store Lawton at the same index, because it's hashing to index 0, so I gotta put it there too. And we'll store his number. Alright, so this is the final setup of our hash table, and we just inserted two things. They happen to map to the same index, and so we put them into a list together. And the reason we needed to save the keys is because when we look up, mom will get taken again by the hash function to this index, and we'll have to look there for which of the values was ours to pick out. And so we need to save the fact that, okay, if you wanted mom, this is the value. Okay, so we need to save the mom string. We need to save the keys. Okay, save the bees? No, save the keys. So lookup is go to an index and find the key that you were looking for and then extract the value. Okay, okay, are you ready? So I'm going to code this up and we're going to do this. So vim hashing example.cpp. I was playing around before this. All right, so let's get this all worked out. First, I need vectors. Then I need lists inside those vectors, and some of my keys are going to be strings. So there we go. And then I need pairs. So I'm going to make a struct pair. It's going to take a string key and a int value. So I'm going to store. Are you ready? Here's my hash table. It's a vector of lists of pairs v, and let's have it be of size 3. Okay, this is my hash table. All right, so now I want to insert into the hash table. V's the hash table. I want to insert mom with 5555555. Okay, then I want to do the same for me and that, and then I want to extract. So lookup in hash table v mom, and maybe I'll print that out. I'll do the same for me. All right, so let's work on our insert into hash table function. It's going to take a vector of lists of pairs, key value pairs, take it by reference, v, then we're going to take a string key and an int value. All right. We can save some space by doing that, and this will just be void. So let's figure out how to do this. So to insert into our hash table, we need to take our key and hash it. All right, so first we're going to get the index. Int index is hash string key. And we're going to make a hash string function now. It's going to take a string and return an int. And I'll just make a super stupid and simple hash function. Everything goes to 0. Okay, you'll have to think a bit harder in your lab. So there's that, and all right, hash string, we're gonna get an index back, and that's the index we need to store this at, so then store the key value pair at that index of the hash table. All right, so we're gonna say v dot at index dot push back, because it's a list of a pair of things. So I should better make the pair first. So pair p equals first the key, then the value. All right. Then we can say push back p. That should do it. And this syntax is equivalent to, if you've never seen it, pair p semicolon p dot key equals key p dot value equals value. Okay, it's just array-like syntax. So there we go. Now we've got it at the hash table index, and now we need to get it out. So we want lookup in hash table, and this is going to return back the value. So it's going to be an int because it's the ints are the values. Then I'll take a vector of all this stuff. I'll just copy it. And we're going to look up the key. All right. So say we were looking up mom. Well, we need to go to our hash table index of mom and pick out the value there. All right, so here's what we do. We need to go to the index in V of where key is hashed to. So again, index equals hash string key, and then we'll go there. Dun, dun, dun. Now why is it unhappy? Oh, never mind. So then we'll go there. So list pair. This is inefficient, but why not? Well, technically, we probably use references. It'll work out. L equals v.at index. Does that actually work? Yeah, cool. So it would copy it if we didn't use the reference, but reference doesn't need to copy it now. So then we need to go through the list now and find our key if it's there. It might not be there. So maybe we can return -1 if not found. Okay, so now we go through the list. So for pair P, let's do pair reference P in L. And we need to see if we found our key. Alright, so if P dot key is equal to the key we're searching for, then we'll return p.val, because that's the value that we wanted to find. If we searched mom, we found it over here. No. We noticed that it was here, so we need to search for this list. And all right, we'll return the 555 number. Otherwise, if it wasn't there, we'll return some special wasn't there value. Okay? So, doing hash table, these three things, these will be there, this one will not. Let's do this. And so it went and it found all these things. So that's essentially hash tables. You just need to make a fancier hash function, obviously. There we go. All right, so one thing I do want to talk about before we go on any farther is, well, a little bit of a sneak peek for your next class that you take. So CSCI 26 is Discrete Math, and here is why you should always use a prime number as the size of your table. So what it does is it helps guarantee that your data gets spread out evenly. So for example, let's pretend we have a size 24 table. What happens when our hash function just keeps giving back a multiple of 12? So, for example, maybe we have a bunch of values that all get mapped to multiples of 12. 12, 24, 36, 48, 60, 72, and our hash function is mod 12, of course. Oh, sorry, mod 24. Hash function. So that means 12 is going to get mapped to index 12, 24 is going to get mapped to index 0, 36 is going to get mapped to index 12, 48 is going to get mapped to index 0. And this isn't uncommon. It's possible to have a ton of collisions like this. So you're trying to store so many things at the same indices. That's bad, because then you have to look through a list. That's a lot of time to waste. And there are several numbers like 12. It's anything that has a factor in common. With 24, which was the size of the table and the hash that we were using. So don't worry, I'm never going to test you on this. This is for your next class. But here's why you should use size 23 of your tree. Gosh, why am I saying tree? I'm thinking ahead, I guess. It's another T word. Size 23 table for multiples of 12. This is what happens there. Because it's prime, it shares no factors. So index 12 is going to go to index 12 again. Index 24, mod 23 now, because that's our hash function, mod 23. Oh, it's going to get mapped to index 1. index 36 is going to get mapped to index 13. Index 48 is going to get mapped to index 2. And you see how there are no collisions yet. It's going to take a while. I mean, it'll still happen because there's only 24 places, or sorry, 23 places. But isn't that nice? Isn't that super nice? Yeah, so only multiples of 23 have the problems here. That's like 0, 23, 46, and obviously that's going to cause an issue, but there are no other numbers that also cause that problem. That's the best we can hope for. Whereas for 24, you've got like 3 and 6 and 12 and all those numbers that have overlapping that will cause collisions like this. So yeah, use prime numbers. That's the thing. And now I think we can get into hashing with lists. Let's see how we're doing on our time. So let's see here. All this stuff I've implemented for you, but let's talk about them. So this is also called separate chaining. So think of it as we're chaining together all of these different lists. Okay, and so a diagram of this in action, again, is, let's make it simpler. Let's go from, let's insert, so example table size 5. So it's got indices 0, 1, 2, 3, and 4. Whee! There we go. And let's store, let's just map numbers to strings or something. Int keys, string values, and then let's insert the following things. 5 mapping to high, 1 mapping to mom, 6 mapping to hello, 25 mapping to blah, and then like 12 mapping to the string with just A in it. Why not? I'm not creative right now. Okay, so with a table of size 5 and we're using int keys, usually, hey, this is a prime number, that's good, we can use the mod 5 hash function to shrink our ints down to the proper indices. And so remember that all these indices start out holding empty lists, okay? These are all holding empty lists. And that's how we start. And so now if we want to insert at index with key 5 the value high, we'll mod 5, get 0, and be like, okay, this needs to change to be this pair, 5 high. Because this hashes to 0, this hashes to 1, this hashes to 1, hashes to 0, this hashes to 2. Alright, so now we will try and add this one. Key 1 mapping to mom. Okay, that's going to go to index 1. So that's our new list there. And then for hello, again at index 1, like, alright, I'm going to add another pair because it took the key 6 to hello. And those are going to be stored in the same place in our table. And then at index 25, or key 25 is going to map to the value blah, and so that's going to hit index 0 again, so I'm going to need to change this to now have another pair, 25 mapping to blah. And yeah, then the next one is we're trying to add index key 12 value A, and 12 gets mapped to index 2. So then we're going to go here and be like, yeah, oh no. The pair 12 and A. So this is our resulting hash table. Okay, we've got 4 indices, and if I didn't make these all contrived, they'd be a bit more spread out, but they're still pretty spread out. We have, if you try and look up 5, we'll first hash it to its proper index, then go to index 0 into the list and be like, I need to search through all these values here until I find 5. If I find it, I can return the value that I'm searching for. So this is how hash tables work in a nutshell, that use open hashing. So you're using lists to store stuff. Okay. So every index has a list. Stores a list of pairs, and that is the key. And I think I want to highlight that in rainbow just to make it clear. All right, so let's see here. I think that maybe I'll do lookup and then I'll come back for the rest. All right, so we've talked about it a little bit, we've programmed it, and so for lookup, this is what happens. We need to go into the table, at the proper index, and get the list, and search through the list. And so think about this from the perspective of what you're trying to do. So pretend you're looking for the value associated with key K. So you're going to go into the table at the proper index and search through the list for K. Okay, so what does that mean? Well, where's the proper index? It's always the hashed value, okay, or the hashed key. So pretend you have a function called hash. And you call that with your key. Okay, that'll give you the proper index, because a hash function always takes a key of any type to an integer. That could be then perhaps shrunken down if you needed it to be. Okay, so that's that. And okay, what else? Once you're there, you now have a list to search through. So to search through the list, just iterate through it. Because eventually, like if it was, I don't know, key 1 is mapped to blah, key 5 is mapped to foo, and you're looking for foo, or you're looking for 5, eventually you'll have a pair where the key associated with it is the one you're looking for. And that's the value that you return. And so the corresponding key, it's K. In this example, at least, until you find K, until you find 5. And yeah, then you just have to return that. And finally, it's possible that you didn't find it. So if you didn't find it, you have to return some kind of not found value. Okay, so maybe that's index -1, empty string, null, for example. It depends on the hash table and your implementation. So if you find it, that's great. Return the value, because a hash table is for associating keys with values. You give it a key and it gives you back the value. And yeah, if you didn't find it, you're going to have to tell the user somehow, maybe throw an exception. Saying that you didn't find it. Okay, so let's talk about insertion and take a couple more minutes on that. So for insertion, again, we have a place that we're looking, and we need to store it in that place. So associate a key with a value, put it in the table. Put it in our hash table. That's a vector of lists of pairs. All right. So we need to first find that hash, find that index. Sorry, not to search through, to insert in. Again, that is for key k, it's hash k, potentially mod size somewhere, depending on how you implemented your hash function. So that's the idea. So, okay, at that index then, you need to add a new list node. And you can put it wherever you want. So for example, in my examples, what I've been doing is I've been putting the next thing that we're inserting after things that are already there. I'm putting it at the end of the list. But maybe for your particular application, things that were more recently inserted are going to be the ones that you're going to look for more often. So maybe that should be at the front of the list if that's how you're going to search through it. Something like that. So somewhere. There's no, you're going to search through everything. So it's up to you where to store that list node. And when we talk about runtime complexity, this'll matter a little bit. So you want to keep these lists small, that's for sure. Okay, so you can put it at the front, put it at the back. Always push it back, perhaps. Maybe that's what you want to do. Okay, at that index, you add a new list node somewhere, and that's essentially it. That list node needs to contain a pair of key value, okay? Because you need to store that key to resolve any collisions. So you might have lists with more than one thing in it, of course. So that's why you store the pair, and that's essentially it. Store that pair and you are home free. Okay? And then finally, let's talk about removal now. It's really not too bad. Again, figure out where you need to go. I haven't talked about it, we haven't implemented it, but it's really not that hard. So you're like, all right, I'm done with key 25. Get rid of it, please. All you need to do is find this list and change it. You see that? So hash the key. So it'll look like this. You'll say remove and then the key. That's how it'll look. And what you'll do is, again, go to the proper index. That is hash of key, and remove the node with that key from the list. Dun dun dun. And yeah, that's essentially where all you have to do is remove the node with that key from the list. And let's see here. Yeah, I think that's all I wanted to say there. You'll just iterate through the list and remove the node using like the erase function on lists, things like that. So that's essentially all I want to show you there. But insertion has another special case that I now want to talk about, because we've talked about removal, we've talked about insertion. There's one more thing that could happen. Okay. it's possible for us to update a key that's already in the list. So this algorithm needs to change a little bit now. Okay? So if we want to change the value of a certain key, and it's already in our hash table, we need to do something instead of adding a new list node. Only if it's not already there. Okay, so if it's already there, then just update the value in place. So for example, if I wanted to insert 25 foo, I would find this and just change the string. Oops. Just change the string to foo. See that? That's how you do it. Okay, so let me update this algorithm really quick, and then that'll be that. Dun dun dun. So, first, figure out first if the key already exists in the table. So we need to do that. So, dun dun dun. Let's just do this very quickly. For pair reference p in v.at index, inside of that list, if p.key is equal to key, then just change the value. And we're done. All right, so we say p.key, p.val equals new val, and then return. All right, nothing left to do. Otherwise, it wasn't in the list already. If the key, that is, wasn't in the list already, add a new node. Okay, so that's the secret. Hopefully that makes sense. And let me update my phone number. And then re-output my number. Hopefully it changes. Oh goody. All right, so that's where I want to leave you, and I'll see you in the next lecture.